Identifying where lone pairs are, so like Lewis structures, that becomes really important when identifying whether something is an electron donating group or an electron withdrawing group, because we will be using that a lot today. In addition to resonance structures, our good old friend resonance, you never get away from it. It's going to become very, very important today. So we're going to be doing some of that, as well as substitution patterns on benzene. So remembering the terms like ortho, meta, and para substitution, as well as electronegativity. So all these things are going to come back in today's lecture. As we continue, electrophilic aromatic substitution. So we have 3 learning objectives, though the last 2 are really combined. But the first one is choose correctly between Friedel-Crafts alkylation and acylation reduction for the synthesis of alkyl benzene. So you previously learned each of those reactions separately. So we're now going to kind of compare them and when you might use the different pathways. And then the bulk of today's lecture, we're going to be talking about electron donating groups and electron withdrawing groups and how that affects electrophilic aromatic substitution. Okay, and especially using resonance arguments. So these kind of last 2 go together, but resonance is important enough that we wanted it to be its own learning objective. All right, so let's start with a little bit of a recap of the generic kind of electrophilic aromatic substitution that you've learned in the past week. So this is sections 13.1 to 13.8. So you have learned in electrophilic aromatic substitution, you have an aromatic ring, such as benzene. That's going to act as our nucleophile. That's why I'm writing it in blue. And then we have some sort of electrophile, usually an electrophile that's attached to a leaving group. Then our nucleophile attacks electrophile. So the pi bond from the aromatic ring is our nucleophile. It attacks our electrophile, our leaving group leaves, which forms a positively charged intermediate. So now our electrophile has formed a bond with this carbon here. We have broken aromaticity, and then we need to regenerate that aromaticity. So our leaving group can act as a base to pull off that proton, which regenerates our aromaticity. So the overall consequence of this is that we have substituted 1 hydrogen with our electrophile, right? So that's why it's electrophilic aromatic substitution, because we've substituted a hydrogen with an electrophile. And you learned a bunch of different reactions because this electrophile can be many different things. So the mechanism is very similar across all of these different electrophilic aromatic substitution. But if you use a different electrophile, that then leads to different products. So even though they're listed, right, as, oh, these are all different reactions, technically they are, because you're getting different products, they're really all the same reaction because the mechanism is the same across all of these different ones. So let's remind ourselves that we use the 4 Ps, right, for our learning objectives. So let's remember the 4 Ps and the ones that we have kind of talked about so far. Okay, so far we've talked about predicting the products, right? So you give the starting materials, you have to tell me what the product is. That's predict the products. We also just went through the mechanism. So part of that was picking out our nucleophile and our electrophile. So for all electrophilic aromatic substitution, the aromatic ring is the nucleophile, and then whatever your reagents are the electrophile. So that's always the same. So that's picking out our nucleophile and electrophile. Sometimes you have to generate that electrophile. And then we had that provide an arrow pushing mechanism. right? So predict the products, picking out the nucleophile and electrophile, provide an arrow pushing mechanism. So you've done all of that for all of these different versions of electrophilic aromatic substitution, including, halogenation or nitration or sulfonation, all of those, right? We have not really done too much on the last P, which is propose starting materials, so SM, starting materials, or reagents, which is like predict the products, but sort of thinking backwards. So I think that this one is one of the harder ones because we're used to thinking in the forward direction, and here we need to think backwards. And so we're going to do a chime-in question to see how we do when thinking backwards for electrophilic aromatic substitution. So in this case, I'm giving you the starting material and the product. So you need to figure out what the reagents are. So this would be propose starting materials or reagents. In this case, reagents. So you have to approach this question a little bit differently than you would approach a predict the product. So again, feel free to chat with your neighbors. Think about what you think it is. Get your answers in. Okay, maybe 10 more seconds. Get your answers in. All right, see what we got. Excellent. Okay, so most people are getting this. You would need chlorine and iron chloride. I can see why some people would think aluminum chloride, right? Because it has chlorine in it, but that is not a source of electrophilic chlorine. So let's just write this out real quick. Go back here. So the question gave you this. And this. Okay, so when I approach this type of question, when you have the starting material and the product, the first thing I try to look for is what changed, right? So if I'm thinking about what changed here, I can notice that we had a hydrogen that's now a chlorine, right? So the thing that changed is the chlorine. And because we know that our aromatic ring is going to be our nucleophile, the reagents that we need to provide must be the electrophile, right? So when I'm thinking about this, what's going through my head is that we're adding chlorine. So that must mean that we're doing a chlorination. And I'm thinking about we need to get the electrophile. So how do you get an electrophilic source of chlorine? You need both chlorine gas as well as that catalyst, iron chloride, which is going to help you make a stronger electrophile to be able to do that. If you only had aluminum chloride, that's the catalyst, not having any electrophilic source of chlorine. Questions about that? Does it make sense? How you kind of have to like think backwards? I think it's a little bit harder, but I think that trying to practice that and going backwards is really, really important to make sure that we understand all parts of the reaction and not just in one direction. Feel okay about it? All right, cool. So that's a little bit of a recap. So now we're going to move forward with sort of different content. So our first learning objective for today is 13N. So choosing correctly between Friedel-Crafts alkylation and acylation reduction for the synthesis of alkyl benzenes. So this is section 13.8. Okay, so this is, again, we're gonna be thinking backwards. So I'm gonna start with, what do we want to make? So what we want to make is an alkyl benzene. So what does that mean? So benzene, right, is our aromatic ring. And then alkyl, so let's say we wanna make this one. Okay, I'm gonna number our carbons here, 1, 2, 3. That's gonna become important later. All right, so we wanna make this. So my first instinct, if we were gonna make this, is, oh, I'm adding an alkyl group. So I wanna do an alkylation. That would be the most straightforward thing. So let me go backwards and think about how I would do that. So remember, this is a retrosynthesis arrow. So that means that we're going backwards. Okay, so we're going backwards, doing an alkylation. What would our nucleophile be? Well, every electrophilic aromatic substitution has the aromatic ring as the nucleophile. So it should just be benzene. Okay, what would our electrophile be? So I'm gonna make sure that I have the right number of carbons. 1, 2, 3. And I would want to attach my carbon number 1. So say I would add a chlorine here. So that's what it would be if I wanted to do alkylation. But this is a huge exception alert. You have to check your work. Does this actually happen? And the answer is that it will not. So we think about the electrophile that we would get from this, right? If we add our aluminum chloride catalyst, we would make 1, 2, 3, right? We would make a primary carbocation. Last time you talked about how primary carbocations are super not stable. It's going to want to do a rearrangement. So this 2 carbon has a hydrogen on it that will want to rearrange to form a secondary carbocation, right? Secondary carbocations are way more stable than primary. So if you tried to do this reaction doing an alkylation, you would not get the desired product, right? Instead, you would use this as, this would actually end up being your electrophile. And that would give you a product that you don't want, right? So you can't use alkylation for this product. So this is where you want to use acylation instead. So what does that look like? We still have the same nucleophile, still just our benzene ring. But now we're going to use an acyl group, right? So again, this part right here, that's called the acyl group. This is acylation. We still have 1, 2, 3 carbons. And acylation is going to avoid this rearrangement product, okay? So when I add my aluminum chloride catalyst, it will do acylation to add in that acyl group like so. So now I have my 1, 2, 3 carbons that are in that linear form. But this is still not the product that I want, right? I still want to make this alkyl product. So now I have to do reduction. And you learned 2 different reductions that you can use. One is the Clemmensen reduction, which is the acidic conditions, right? So if it has HCl in it, that means it's under acidic conditions. Or you can use the Wolff-Kishner reduction. Which is under basic conditions. So this KOH right here is a base. So that just means that it's under basic conditions. So you can use either of those. So Clemenson or Wolff-Kishner. These are 2P reactions, so you don't need to know the mechanism of these reactions. And all that it does is that it takes away the acyl group, like the carbonyl, without losing any carbons. So we still have 3 carbons, but now we have 2 hydrogens here instead of that carbonyl. Questions on that? I know that that's a little bit confusing, but I guess the biggest thing that I would say is that when you're trying to differentiate between these 2 pathways is first think about what the easiest thing to do would be, right? If I see this, I would want to do an alkylation because we're adding an alkyl group. But then once you do that, you always need to double check, right? Go in the forward direction and be like, okay, what electrophile would I actually make? Are rearrangements possible? Because in an alkylation, if a rearrangement can happen, it's going to want to happen. If you can make a more stable carbocation, it's going to do that. And so that is why this is always going to happen. So that then, if that doesn't work, then you do this acylation reduction. Questions? Yeah. Oh, yeah, you can choose either one. So yes, like on an exam, if you were proposing a route, choose one of them. You don't need to do both. Yep, because they are both totally fine. Yep, good question. Other questions? I know it's a little bit challenging. Yeah. Yeah, that's a good question. So when is alkylation more beneficial than acylation reduction? So whenever there's not a rearrangement, it's better to just use alkylation because it's 1 step instead of 2 steps. But technically you could do acylation again if you wanted to, it's just more steppy. So it's just more efficient to do the alkylation if you can. But when you can't, then you have to do acylation. Yeah, good question. Can you use sodium hydroxide instead of potassium? Probably. I'm not super familiar, to be honest. Like, they're usually very similar, though. I would be surprised if you couldn't, but I don't know off the top of my head, to be honest. Other questions? Kind of makes sense, right? Try alkylation first, but if you're going to get a rearrangement, do acylation instead. Okay? All right. So all of these, right, we have been doing benzene as our nucleophile, just benzene. But now we're going to talk about what happens if it's not just benzene. So what if our nucleophile isn't just benzene? So this is going to be most of the cases where it's not just benzene. So now we're going to have an aromatic group that already has a substituent R. So we call this a substituent. And R can be a lot of different things. So we're going to talk about what those different things are. But for now, we're just going to label it as a generic R. And this is where we got to remember the terminology is when you already have one substituent, the carbon next to that is the ortho position, and then the meta position, and then the para position. So when we do an electrophilic aromatic substitution, I'm just going to draw our generic electrophile here, because it could be any of them. We have 3 possible products. So I'm always going to draw my R group on the top, but I could have my electrophile in the ortho position. I could have my electrophile end up in the meta position. Or I could have my electrophile end up in the para position. Okay, see how there are 3 different products, right? So I'm always keeping the R group at the top. And we're just changing where the electrophile is attached relative to that R group, okay? So you are not going to make all three of these products for every reaction. So we need to talk about how do you decide which one or which ones is or are favored. So that is what we're going to talk about for the rest of the class period today, because it's a little bit complicated because it depends on what R is. So these are actually two different learning objectives that we're going to kind of combine, or we're going to talk about at the same time. So we're going to explain how electron donating and strongly electron withdrawing substituents on an aromatic ring affects both the rates and regioselectivity of EAS. So this is sections 13.9 through 13.13. So regioselectivity just means which of these three products are we making, because we're attaching at different positions. So that's our regioselectivity. And then it goes along with this, but we separated it out into a different learning objective, 13P, which is to illustrate how substituents affect rate and regioselectivity using resonance arguments. So those are really the same thing, but because we really wanted to emphasize that you need to be able to draw the resonance structures, we made resonance structures a different learning objective. Okay, so this is a very large, like, two learning objectives. So we're gonna kind of break it down into these different parts. So let's start with strong electron donating groups. I'm just gonna abbreviate this, so electron donating. And then I'll also abbreviate electron withdrawing groups. Okay, so strong electron donating groups. And we're first going to talk about regioselectivity. So this is section 13.12. All right, so strong electron donating groups. So this is where knowing how to draw Lewis structures is very important, because identifying if something is a strong electron donating group means that you need to be able to tell if there are lone pairs on the atom attached to the ring. So this methoxy group is an electron donating group because it has a lone pair, or lone pairs in this case, right, which is able to push electron density into the ring via resonance. All right, so now we're going to draw a bunch of resonance structures. So let's remind ourselves how to do that. So when you are drawing resonance structures, you always need to start the arrow on electron density, as always. So that means starting on a lone pair or starting on like a pi bond. So we're going to start on the lone pair, and we're going to push that electron density to form a double bond between the carbon and the oxygen. But then that would make this carbon have too many electrons. So we need to break a bond. So we can break this pi bond here. And we're going to dump that electron density onto the adjacent carbon. Okay, so we're going to use resonance arrows to remind ourselves that this is what resonance arrows look like. So when I am drawing resonance structures, the first thing that I do is draw what didn't change. So what did not change were these two pi bonds on the right side of the molecule. But then I now have a double bond between my carbon and my oxygen. I still have one lone pair on my oxygen, and it is now positively charged. And I dumped 2 electrons onto this carbon on the left, so that is now negatively charged. Okay? We're going to do it again. So we're going to start where the electron density is, which is the lone pair, where it's negatively charged. We're going to push it on the other side, so it's going to form a double bond on the next 2 carbons. If I pushed it back the other way, we just go backwards. So I want to keep going forwards. But now this carbon right here would have too many electrons. So we need to break this double bond. So we're going to break that double bond and dump the electron density on the para position carbon. So just make sure that you're always starting your arrows from the place of electron density, and that your electrons are not hopping all over the ring. All right, what didn't change? Well, this pi bond on the right side didn't change. My double bonded oxygen methoxy group didn't change, so we're going to draw that first. Okay, so then what changed on the left side of the molecule? Well, I now have a double bond kind of over here, and I put 2 electrons on the para position, which should make it now negatively charged. Okay, resonance structure is super important. This is really hard. This is something to practice. This is something to ask about in office hours or OLS. This is a really, really important concept. Okay, we're going to do this one more time. Again, we're going to start from the lone pair where it's negatively charged, where the electron density is. We're going to push it to form a double bond on the right side of the molecule now. And then we need to break the pi bond. We dump the electron density onto the carbon. Okay, what didn't change? Well, now the pi bond on the left side of the molecule didn't change. My double bonded methoxy group didn't change. But now what did change? So bottom right, I just added a double bond. And now the ortho position on the right side of the molecule got 2 electrons on it, which makes it negatively charged. Okay, does it make sense how I constructed those resonance structures? Yes. So it's negatively charged because they have, okay, so if I were to draw out so this carbon has a hydrogen attached, carbon, carbon, and a lone pair, right? Okay, so when we count formal charges, right, anything that's in a bond counts as 1, right? So we kind of think about like, okay, there's 2 electrons in this bond, but one of them goes to this carbon and one of them goes to this carbon, right? So we have kind of 1 electron here, 1 electron here, 1 electron here, and 2 electrons there. So if we look at the periodic table, carbon only wants 4, but if you have a lone pair, it actually has 5. So it has more electrons assigned to it than normal, basically. Like if you have 4 bonds to carbon, it's neutral. Adding 1 extra electron makes it negative. Does that make sense? Yes. You got to remember, like when drawing Lewis structures, right, that we have to make sure that we don't draw hydrogens if they're implied, but if it helps you, draw them every time. That's absolutely no problem. It's a good strategy. Yep. Good question. Okay. We cool with resonance structures? Yes. So they are equivalent, but they are technically not the same because those are not like, it's a symmetrical molecule, so they are equivalent, but this carbon is different from this carbon. So like you can do either, but they would give the same product. Yes, because they are different, because it's a different carbon. Because if I were to number the carbons, right, they would be different. Okay, so what does this mean? How does this help us? So now let's think about, all right, so I'm going to draw down here. Whenever we have an electron donating group, we can look at, this is an ortho position, that's over here. This is a para position, which is down here. And this is the ortho position on the other side. So all of those have some partial negative charge, right? Because we have a resonance structure that has a negative charge on it. And remember that resonance means the actual structure is an average of all of these resonance structures. So we have some delta minus, delta minus, delta minus. So there is more electron density on these ortho and para positions. So again, let me just label them. This is ortho, ortho, meta, meta, and para. Okay, so these resonance structures told us that we have extra electron density at the ortho and para positions, right? Extra electron density at ortho and para, because the resonance structures show negative charges at those positions. So now you got to think about, in this reaction, right, the electrophilic aromatic substitution, the aromatic ring is the nucleophile. So if we have electron density at those positions, that means that it is more nucleophilic at those positions. Right? Because nucleophiles lend their electrons. So if they have more electron density, it makes it better at its job. So if those positions are more electron dense, they're going to be more nucleophilic. That is where the reaction happens. So, for example, I will use a different electron donating group just as an example. So here, again, I have a lone pair on the atom attached to the ring. So this is an electron donating group. If I were to then do, say, a bromination, this is an electron donating group. The most nucleophilic positions are ortho and para. That means that I'm going to get the ortho and para products. Again, I'm going to keep my substituent always in one position, so the up position. I'm going to put my bromine in the ortho position. Or alternatively, I can put my bromine in the para position. So this is our ortho, this is our para, and you actually get both of those. Okay, so the ones that are most nucleophilic are the most reactive, and therefore you get both of those products. Question? Nope, you're going to get both in this case. Yep. Does that make sense? Right? Which positions are the most nucleophilic? Which ones are the most reactive? Because it is the nucleophile. Therefore, you get the products that are most nucleophilic, right? So in this case, it's going to be ortho-para, because those are where the electron density is. Yeah? So this is for strongly electron donating groups, okay? Look for that lone pair on the atom attached to the ring. Not just a lone pair anywhere in the molecule, attached to the ring, because otherwise it can't do this resonance stabilization, okay? Okay, that's electron donating. So now let's talk about electron withdrawing. So now we're going to do strong electron withdrawing groups. Again, we'll talk about regioselectivity first. This is section 13.13. Okay, so strong electron withdrawing groups, instead of having things that can push electron density into the ring, we're going to use things that can pull electron density out of the ring, like a carbonyl, like a ketone, for example. So this is an electron withdrawing group. So this electron withdrawing group pulls electron density out of the ring. Okay, so again, we're going to draw a bunch of resonance structures. Okay, so we are now going to break the closest pi bond in the aromatic ring. We're going to pull it out, and that goes up into the carbonyl. Okay, so this is why it pulls electron density out, is because that oxygen is an electronegative atom. It wants that electron density, so it pulls electron density out of the ring. So again, I draw what did not change first. Now there's going to be a double bond, oops, up here, negatively charged oxygen. And I left the ortho position on the left side deficient. So it should be positively charged now. Okay. Can draw another resonance structure. We just kind of push that pi bond over to fill the deficiency. So again, I start with the things that don't change. And then what did change, I moved the pi bond to the left, and now my para position is deficient. So it's lacking electrons, so it's positively charged. And then finally, can push one more. So starting with what doesn't change, I still have this negatively charged oxygen. I made a new double bond bottom right, and now my right side ortho position has a positive charge. Okay, so what that second learning objective, right, that learning objective 13P, this is what we're talking about. So learning objective 13P, we want you to be able to draw all these different resonance structures. Yes.
So how can you tell the difference between whether an oxygen is going to be an electron donating or a drawing group?
Yep. So it's where is it connected, right? So up here, the oxygen was directly connected to the ring, so the lone pair can push down into it. Here, if we draw where the lone pairs are, they're up here, right? I can't push that into the ring because it's not attached to the ring. Because then that would make the oxygen positive, right? And like electron deficient, which it really does not want to be, right? Because oxygen is an electronegative atom, so it wants to pull the electron. Yep. It doesn't want to be deficient ever. Yes. Because even when it was positively charged before, it was not electron deficient, right? Like it was still had the correct number of bonds. Yeah, the correct number of bonds. Good question though. Okay, so what does this mean? So once again, we can think about generically, when we have an electron withdrawing group, our ortho positions and our para positions have delta positive, right? Delta positive, because that is where the positive charges are in these resonance structures. So here we have it in the ortho position, para, and ortho. So that means that we have less electron density, or it's less nucleophilic at those ortho and para positions, right? So if it's worse at its job in the ortho para positions, then relatively meta is where it's going to go. So therefore, meta are the most nucleophilic sites. And it's not because it has extra electron density, it just means that it's not as bad, right? Because we're still pulling electron density out of the ring, but relatively, it's still more nucleophilic than the delta positive orthoparasites. So an example of this, again, I will use a different electron withdrawing group just to give you an idea that it does not need to look one certain way. So this works in a very similar way. So this is an electron withdrawing group. Now I can do an electrophilic aromatic substitution. Let's try nitration this time. Why not? So now in this case, our electron withdrawing group is going to stay on the top, and we're going to get the meta product. So now for meta, there's only one, because if you put it on the other side, it's equivalent. It's the same. Okay. So to recap our regioselectivity, if we have electron donating groups, those are going to be ortho-para directors because it directs reactivity at the ortho-para positions. And then for electron withdrawing groups, we call those meta directors because it's directing reactivity to the meta position, right? For the resonance reasons that we just talked about. Okay, so those are strong donating, strong withdrawing. So that's regiochemistry. So let's talk about rate for a second. We've already rationalized through the rate, so let's just formalize it. So section 13.12 talks about our electron donating groups, right? So we talked about how electron donating groups push electrons into the ring, so it makes the nucleophile more nucleophilic. So if you make a nucleophile better at its job, your rate of reaction should go up. So therefore, it is called an activator. In contrast, if you have an electron withdrawing group, that's pulling electron density out of the ring. So that makes our nucleophile less nucleophilic. So if we make the nucleophile less good at its job, you better bet the reaction rate is going to go down. It's not as good as being a nucleophile, so our rate of reaction goes down. So this is called a deactivator. Okay? You rationalize it in a very similar way though, right? Are you pushing electron density in? Are you pulling electron density out? Does that make the nucleophile better at its job or worse at its job, right? And where is that negative charge in order to, in order to rationalize the regiochemistry? Is it a better nucleophile at that position, or is it a worse nucleophile at that position? Questions on the strong electron donating, electron withdrawing? Yes. But the pair position still has that partial negative charge, which makes it more nucleophilic. Because of the resonance. Yes, because of the resonance structure that actually puts the negative charge at the para position, and it always skips the meta. Yes. Okay, all right, so let's talk about the slightly more challenging, which is the weak electron donating groups. Which is section 13.10. So an example of this would be an alkyl group of some sort, so like a methyl. So this is a weak electron donating group. So this one does not have a lone pair for resonance, right? So we can't do the same trick of just pushing the electron density into the ring at the beginning. So instead, we need to look at the intermediate. So when we do the first reaction, or the first step of the mechanism, excuse me, we could either have ortho, meta, or para attachment of that electrophile. And so in order to rationalize this, we need to draw resonance structures for the intermediate for all of them. So if I'll do ortho first, so we have our methyl group. If we attach this in the ortho position, we have our positive charge over here. Our leaving group is our counter ion. I can draw a resonance structure where I stabilize that positive charge and push it around the ring. Again, what didn't change first. And then I draw what does change. I moved the positive charge to the other side. Can do it one more time. Push the positive charge around the ring. Draw what didn't change first. Then draw what did change here, here. My positive charge ends up here. Okay, I'm going to compare that to the meta case. Where I attach to, oh, sorry, I have it drawn on the other side for where I had it drawn before. Like so, positive charge here. Can draw a bunch of resonance structures again. So for both cases, we can push the positive charge around the ring in 3 positions, but they are not equivalent. Just draw my last one. So what didn't change? That didn't change. Here, here, here. Okay. Now we have to look at the stability of these carbocations, right? So in my ortho, this first one, is that a primary, secondary, or tertiary carbocation? Ones and twos, yes. Secondary. Next one. Secondary. Next one. Tertiary. Okay. What about for meta? Secondary, secondary, and secondary, right? So the fact that we have a tertiary carbocation here gives us additional stability, right? Because tertiary carbocations are more stable than secondary. So I also want you as a challenge to draw the para. I will include that in the notes, but I want that as my challenge to you because it's the same as the ortho. But tertiary is greater than secondary. Therefore, our alkyl groups are also ortho para directors. Okay? So we will recap this next time, but good job as we go through all the regiochemistry.